Hey everybody, welcome to this Fiveable AP Physics 1 live stream. Today we're going to be focusing on circuit components, voltage, current, resistance sort of stuff. And yeah, let's get started. Just as a general reminder, if at any time you have questions or comments or want clarification on something, please just throw it up in the chat or use that ask a question button, and then we'll do my best to answer it as quickly as possible. Also, check out Think Fiveable, I can talk, right? For all of our social media stuff and our weekly stream calendar. So it's Wednesday, it's Science Day. Right now it's Physics 1. Also, every Wednesday at 1 o'clock, for the foreseeable future, we're doing a Q&A session for physics. Any questions, any topics, and we'll work our way through that for at least the next couple weeks until we get a handle for how this school closing crazy situation is working on it. I know my students are looking for a ton of extra resources, so this is one way we can help out with that. Right? And of course, if you're taking other AP classes, check out other options, Calc, AP, Lit, et cetera, et cetera, et cetera. All right, so our plan for today is kind of starting with the basics. I know a couple of you guys are just at the entry level for this. Have any of you guys actually covered circuits as a whole in your AP class yet, or is this still brand new stuff? Starting them now, okay. All right. Brand new. Okay, cool. So my kids in my AP class have not covered circuits 8 either, so they're pretty much at the same point you guys are, which is encouraging for me as a teacher. So we're going to basically start off with just basic definitions. What's a circuit? What do we measure in a circuit? What tools do we use to measure them? And then do a little simulation where we can figure out the relationship between a couple things, voltage, current, and resistance. Then we'll talk about resistance in a wire, which for at least my perspective is usually a couple-day lab period, and then some practice problems and Q&A at the end. So let's dive in and get started. So I guess the first question is, what's a circuit? How would you guys define the word circuit, or be able to recognize what a circuit is versus what a circuit is not? So take a moment, ponder, and throw up some comments in the chat. I'd love to see what you guys are saying about what a circuit is. All right. So as we're pondering, we're quiet in the chat, and that's fine. Hopefully you guys were thinking about it. But basically, the simplest definition I can make is a circuit is a closed path from point A to point B that allows charge to flow. Okay, Jen, you said the flow of electrical currents. Yeah, that's the right idea. We're going with, instead of electrical currents, because that sounds really fancy. It's correct, don't get me wrong here. But really, charge is the best option. Where we're going from one point to another and charge is flowing through. For those of you guys who haven't done the Coulomb's law, electrostatics sort of chunk in there, when I say charge, really I'm talking about positive charges like protons or negative charges like electrons flowing from one point to another. Okay? And they've got to be able to flow in a complete loop. If they can't get it in a complete loop, it's not a circuit. It's just 2 points. Okay? You can imagine this is the real life picture, I guess, as best we can call it. And the picture on the right is a circuit diagram or circuit schematic. It's a nice, easy way for us to draw what's going on in a simple, organized way. So you've got a battery here. That's a long line, short line, long line, short line. You've got a switch, which is the open, slanted sort of thing. And you have 2 lamps. light bulb A and light bulb B in there. You can imagine right now, with this switch being open, there's no way for electricity to get through or for charge to get through back to the battery. There's not a loop here. It's just simply a wire connecting to the light bulb, but nothing comes back. And because nothing comes back, we don't have a circuit yet because it's not a closed path. All right, that makes sense? So closed path in order to make a circuit. Let's mess around a little bit now and try to measure some things in a circuit. So I'm going to kill this for a second. Can I do this without breaking it? We'll find out. Unfocus. Close the video. Keep my face on here. Okay. Share. We want to share the lab. Okay. So hopefully, there we go. All right. For those of you who haven't used Phet before, Phet, P-H-E-T, there's links to this in the slides that are attached to the event. So I strongly encourage you guys to come and take a look at these later on. This is a virtual lab for building circuits. And this is something that I'm going to give my kids on there, depending on what our school decides to do for this. But this is one way they're going to experience circuits, even though I'm not sitting down face-to-face with them. So I'm going to build a really simple, basic circuit. I got a battery. I've got some wires. And I probably should put something in there for that to go to. Let's pick a light bulb. So I've got some battery. I got a wire. Oops, I should connect the wire to the right thing. Goodbye. Connect the wire to the right thing. And then as we get around here, we'll actually make I'll put a switch in. Switch looks good. Make a circuit for us to work with. All right, and there we go. So right now we got the circuit. It's open right now. I then close it, and lo and behold, the light bulb lights up. We have used electricity to make something light up. Right, now this is a super simple circuit, which is good. We're going to start simple here. I don't want to get too crazy, but let's take a look at what's going on here. So in essence, we have electrons. Sorry, let's do conventional current. Charge flowing out of the battery, going through the light bulb, and back to the battery. Right? And if I open the circuit, nothing happens. No charge can flow through it because it's stuck. It can't go anywhere. And it tells me very nicely, the switch is open, and now it's closed. We can have the circuit work. All right, so in a circuit, there are three big things that we're going to try to measure: voltage, resistance, and current. Right? So voltage, we get to use this wonderful thing called a voltmeter to measure. You guys may also have multimeters in your classrooms, which basically merge a lot of these different things together. So voltage, I get to put one probe around the thing I want to measure, and it tells me, oh, that this battery has a voltage of 9 volts. Common things, your cell phone works off of 5 volts. A normal AA or AAA battery is 1.5 volts. The wall outlets, assuming you're in the US or Canada, is about 120 volts. If you're in Europe or the rest of the world, it's about 240 volts. So voltage is kind of the measure of how much energy we have to work with. It's not the same thing as energy, so please don't quote me on saying that voltage is energy. They are not. They are similar to each other. But the more voltage you have, the more energy we have to use in a circuit. The next thing we can do is measure the current. Current works kind of like current in a river or through a hose or something like that. The more current you have flowing through it, the more water flows through a hose, or in our case, the more charge flows through the circuit. Current is measured in amps. That's what the capital A stands for. And in this case, we have to connect this meter, this is an ammeter, into our circuit in order to measure the amount of charge going through. And the more charge we have going through, the more that goes up. And then finally, the last one is the resistance. They do make meters for measuring the resistance. but typically they're pretty bad. I have not found a good one that I like using in my classroom yet. So while we could do that, a lot of times we're going to calculate out what the resistance is going to be. And we're going to cheat a little bit here. So I'm going to turn this on. Checking the values box tells us all the values here. So this is 9 volts for the battery, 0.9 amps for the current, and this light bulb is 10 ohms. All right, now let's see how mathematically creative we are late on a Wednesday night here. I should be able to calculate some sort of relationship between voltage, current, and resistance. Anybody find a pattern in how I can get voltage, current, and resistance mathematically to make sense, to click together here? Yeah, so Katie says Ohm's law with a question mark. That is exactly the relationship we're looking for. So Ohm's law is named after Ohm, who is a very famous scientist. He did a lot of work with electricity. And yeah, as Katie put in the chat right there, R equals V over I. So 10 ohms, our resistance, is equal to the voltage V divided by the current I. Now, why does I get the symbol for current? I don't know. It's just the way it is. There's no nice, easy way to explain that. There's a couple stories about who was writing down symbols and they got to I, but you'd think C would be a better choice, but no, it's capital I. So R equals V over I is our equation here. That means that resistance is equal to the voltage divided by the current. So if I were to increase the resistance, keeping the voltage the same, this means that the current needs to drop. And you can see the current on that ammeter is dropping as we go through. If I make this at 90 ohms, for example, the current drops to 0.1 amps. Basically nothing going on there. Okay? Big resistances mean small currents. And that is what Ohm's law basically is telling us. R equals V over I. The resistance is the voltage divided by the current. If the resistance gets big, the current gets very small. They are indirect relationships to each other. All right. And if you take away nothing else from this little montage, that is what you've got to take away here. Resistance and current are opposites of each other. When one's high, the other one's low, and vice versa. All right. That makes sense? All right. Cool. Good. Awesome. Okay. So let me pause this for a second here. I'm going to go back to the notes page. So give me a few minutes to switch back over. Boom, boom. Chrome tab. That one. Go. Boom. All right. So we left off right here. And analogies. I like analogies a lot for when I'm teaching my kids. I mean, preface this by saying it's not a perfect analogy. It is not exactly the same, but it's good enough for what we need to do here. So if you want to picture water coming out of a tank or coming out of a hose or something like that, a hose works really well. Turning on the water at the spigot, there's pressure, there's energy in the water that wants to get out. The more you open the spigot, the more water you get flowing out. That's kind of like the voltage. Voltage is kind of like the push or the energy given to the charges as they flow out. And the more energy they have, the more voltage they have, the faster they're going to come out of there. Okay? Current is like the amount of water that flows out of a hose. And the more that comes out, the better, the higher the current. And resistance is kind of like that kink in the hose. If you take a hose and you put a couple loops and wrap it up really well, you're not going to get much water coming out of it because all the water gets stuck inside the hose. That's resistance. It's opposing. It's stopping the current from going through. To put it in different terms, resistance is kind of like friction, but for electricity. It's stopping the flow going through there. Okay? And then this little picture here I really like, where it's the little guy stuck in front here. The amps are measuring current. So this is current trying to get through this wire. The volts are the guys pushing on him, trying to make him go through. And then ohms are the ones that are trying to stop it, trying to slow down that current going through. All right. Now, depending on the situation, depending on the application, sometimes we don't want very much current going through something. Current is essentially how much charge is going through. Too much charge could lead to things like it heats up, or it starts a fire, or it just fries our electronics. It could be some pretty bad things. So resistance is useful. Resistance is very useful at certain times. For example, my cell phone doesn't want to have a ton of charge going through it. If I do that, my cell phone tends to heat up and start catching on fire or breaking or just stopping working. It's not a good thing. But with the right amount of charge going through it, roughly 1 amp maybe to charge it, it works really well. 5 amps would kill it. 1 amp, 2 amps, that would work pretty fine. Okay. Another example is our bodies. Our bodies are really good at using electricity. That's how our nervous system works. That's how we sense things and experience the world. But too much electricity is dangerous. Our hearts, if you get zapped too much with, let's say, a taser or some strong electric field, it can throw off the rhythm of your heart, which is really bad. Fortunately, our skin is on the order of millions of ohms, which is a massive resistance that keeps most of this electricity out, which is why if you ever seen somebody need to use the paddles, use the AED machine to shock somebody's heart back into rhythm, that has to use huge amounts of voltage to get the charge through our skin and to make it work well. Okay. So depending on the situation, high voltage, good or bad, high current, good or bad, and high resistance, good or bad, depending on what we're trying to do. But the big thing is these three things work together to describe and let us make circuits be the things that they need to be. All right. So that being said, little aside, let's jump to the math. Let's see. We did one of those. I'm going to come back to the other one in a second here. All right. So equations. This is the electricity chunk of your reference tables. And depending on what you've done so far with circuits and other electricity, some of these may look really familiar. Some of these may look like it's Greek because some of it is. So going down the list here of things that's going on, the first equation deals with electric force. This is Coulomb's law. This was something that I would typically cover with my students before we get to circuits, but you might not have. This basically lets us talk about our charged objects, Q1 and Q2. Are they attracting each other? Are they repelling each other? And how much force is going on here? Right below that, we have the definition of current. Okay? Current, capital I, is equal to the charge, the amount of charge going through delta Q, a given point in a given amount of time. So Q over T, charge over time, gives us current. And the more current, the more charge. And the less current, the less charge. Right? We also have down here, I equals delta V over R. This is Ohm's law. Granted, it's not the way that Katie said it. It's not R equals V over I, but it is I equals V over R. Same exact equation. And we'll be using it in pretty much all of its forms. There will be times where we'll have to rearrange this to R equals V over I. There's quite a few times where V equals IR will be the best option. And then, of course, I equals delta V over R. Again, depending on what we're trying to solve for and work in there. Okay. And I guess you could say the current is, nice, Ryan. Yes, it is. Oh, bad physics jokes are good. The last one here is the power equation. P equals I delta V. Okay? Power, the energy over time, or the rate of work, is equal to the current times the voltage. We're going to use that one quite a few times. We're also going to combo that with Ohm's law. And for example, sub in this I for that I and get V times V over R, V squared over R. Or we can get I squared R or IV. So different power equations, again, depending on our use cases on there. All right, what do we got? Questions? Okay, so Jenny, you asked units for current. So current, when I'm going to use it as a variable in a problem, it'll be capital I. When I'm talking about the units on there, I would either do a capital A if it's amps or MA if it's milliamps. And that kind of gets down to, are we talking about a question in the multiple choice sense or the free response sense, or are we talking about a lab situation? For my kids, when we're doing circuit work in a lab, almost all of our readings are in milliamps. And then they'll have to convert that to amps, 10 to the negative third. Amps is 1 milliamp in there. But the symbol we're going to use is I for all these things, and then the unit's going to be amps or milliamps or something like that in there. And I hope that clarifies that a little bit. The last two equations on the bottom here, RS and RP, these will be our subjects for the stream next Wednesday. And that is resistance in series circuits and parallel circuits. So this is a preview. There are two different kinds of circuits you can make. Series, where there is one path for the current to go through the circuit, or parallel, where there are multiple paths for the current to go through the circuit. And they have different rules for resistances based on the type of circuit you have. Again, we're not going to get into that today, but that is next week's stream, a week from today, are those last two equations. All right, now, so we've got current, charge over time. We've got voltage, the push on the charge or the energy of the charge. And we've got resistance, V over I, Ohm's law, the opposition, the holding back of that charge. Well, that's great, but there's one more resistance equation sitting right here. And this one has some weird sort of letters here. It's got this almost like a P thing, but it's not quite a P. We got an L and we got an A. And if we're looking at this, resistance is rho. Rho is resistivity. This is the Greek letter rho, by the way. It looks like a P. It's not a P. It's a rho symbol. That is the resistivity. This equation, R equals rho all over A, lets us describe resistance in terms of materials. At some point in your career as a student, you've talked about insulators and conductors. Whether it's in elementary school, middle school, oh, this wire conducts electricity. This piece of cotton does not. This metal's a really good conductor. This one's pretty terrible. That sort of thing. Resistivity, that rho value gets into that idea of what's a good conductor versus what's a good insulator in there. So let's take a moment and dive into this equation, this R equals rho L over A equation, a little bit deeper. So I'm going to pull up another simulation. So give me a minute to switch the screen, and then we will go from there. Chrome tab. I need resistance in the wire. Come on, there we go. All right. So admittedly, this simulation is not as cool as the other one is, but it's one that works. Again, depending on what your teacher is going to do with this topic, there are a couple of really cool labs you can do with resistance and rho L over A equations. A really cool one is you'd use Play-Doh and you mold the Play-Doh into different lengths and different sizes, and you see how the resistance changes. I do one with different lengths of wire and see how the resistance changes there too. But basically, the gist here is the resistance is stopping charge from flowing through the circuit. All the black dots in this material are kind of like, I guess the physics term is a hole. It's an area where an electron enters and doesn't leave. You can think of it as elements in there or atoms in there that just, hey, I want an electron. I'm going to hold on to it and not let it go anywhere. And the bigger this gets, the more resistance we have. The harder it is for charge to get through it. The lower I make it, the easier it is for charge to get through it. And we see that R just shrinks down to nothing when that resistivity is very low. This is an example right here of a great conductor. This could be copper or gold or silver or, well, what else do we make wires out of? Those are probably the three big ones. Aluminum, maybe. Especially copper. Really low resistivity and makes it really easy to get current through. Okay? Something on the other end of this with a really big row would be a really good insulator. Some sort of thing that would hold on to that charge really, really, really well and not let it go anywhere. All right. Now, depending on your course and stuff like that, the AP exam doesn't provide you a nice table of resistivities. But at least for my kids, I teach out in New York, and our Regents exam, our state exam for physics, gives a bunch of tables with values and stuff like that. So they could be asked to say, okay, what's the best conductor out of this list of materials? What's the worst conductor out of the list of materials? And that really depends on this resistivity value. The bigger it is, the worse of a conductor it is, and the smaller one, the better conductor it is. Okay. Then the other options, length, if I crank L, make it really big, we get a really big resistance. Long wires are harder to get through than short wires. Okay? Short wires are really easy. And area, this one we're looking at R1 over A, so indirect or inverse relationship. A big A makes it easy to get through. And a small a makes it very difficult to get through. Okay? This is another good example of going back to the garden hose analogy. A small a would be like a garden hose. A big A would be like a fire hose or a water main or something like that that's going to let tons more water get through. Marshall, yes, that's one reason we use fiber instead of copper to cross oceans. The other reason is speed. Even the best possible conductor with the lowest possible resistance still slows down the transmission of information a little bit, still slows down the flow just a smidge. And light is always faster than that. So, but yes, that's exactly why we use fiber for that. Or sometimes if you're looking for a very specific audio application where you want really good quality sound, you'll use a certain metal instead of a different metal to do that. As far as the area one goes, we see this in our houses. And if you've done any sort of construction, you may know that there's different sizes of wires in your house. The one coming in from the street is huge. It's got a big honking area because it needs to let a lot of electricity through it. Then it splits from your panel box and goes into various circuits. Maybe one for your kitchen, one for the bedroom, one for the living room, sort of stuff like that. Those wires are much smaller. And depending on what the contractor is expecting you to plug in, they may use a bigger wire or a smaller wire, depending. For example, my kitchen has bigger wires than my living room does because I have an electric stove and I've got a microwave and I've got stuff like that that's going to draw a lot of electricity. I want to make sure more electricity, more current can get to that instead of, well, my bedroom is going to have a light and maybe a TV, and that's about it. So keeping that small, I don't need giant wires for it. Small wires will work equally well. That's also why for things like cell phone chargers, I pull this out, we use tiny wires because you're not using not needing a ton of current through that. You can get away with very low areas because you don't need a super low resistance with it. Is it better? Maybe, but I don't think anybody's going to walk around with a giant, super big cell phone charging cable because, well, you don't need it. All right, so lots of tangents there. R equals rho L over A. Resistivity tells us the material. L, length of the wire, more length, more resistance, less length, less resistance. And A for area, more area, less resistance, less area, more resistance. All right. questions so far? Can a resistor completely stop current? Ooh, that's a good question. I would say it depends on what you mean by stop. Like, for example, me grabbing onto my cell phone cable here and connecting the pins. I am actually letting a tiny, and when I say tiny, we are talking 10 to the negative 7th, 10 to the negative 8th amps of current going on here, going through there. For all practical purposes, that's 0. But in reality, it's not. So saying that it would completely stop it, yeah, I would say that right now I'm completely stopping it. Or, hey, the air right now is completely stopping the current from going from point A to point B because it's an open circuit. In reality, is there a tiny, tiny, tiny smidge going through? Possibly. But would that be something that's going through everything? It's tough to tell. As far as a circuit going through, we're going to say it completely stops if you break the line or if you disconnect the wire in there. But even if you were to take the biggest resistor that you can, which typically would be in the millions of ohms, 10 millions of ohms, and put it in the circuit, you may get a very, 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 very small amount of current going through. Simply because if I do I equals V over R, I'd have to put an infinite amount of R into this equation. So infinite R would mean 0 I. But in reality, we're going to say that 1 over a million or 1 over 10 million is practically 0 for anything we're concerned on. So, yeah, other questions? All right. Okay, so if you guys have more questions, please ask, but I think we're going to jump on and do some practice questions. Yay. All right, so these I stole off of some old AP style exams. They're going to be pretty close to what you might see on an AP test as far as the multiple choice goes. And then we got a free response one after a few of these. So take a minute, take a look at the question here. We've got 2 circular loops, radius A and B. They are in the plane of the page. The total resistance of the wire of loop radius B is R. What's the resistance of the wire loop of radius 2B? Okay, so I had 1 vote for D, for R. Well, you know, that's not a bad guess. As I think about it, I'm realizing that I made a mistake on this slide because my answer will not be the answer I thought it was going to be. So yay for being human. Bad for not checking my work beforehand. But yeah, so let's talk about what's going on here. We've got a circle, right? These are moving in circles around here, and they're loops of wire. So they're the same kind of wire, and we've got different circumferences is the right term we're looking for here. So we're looking at R equals rho L over A. In fact, let me see if I can switch this over to my scratch pad so I can write this out for you guys. Where is my video feed? There we go. That's the one I wanted. Please work. Maybe, maybe, maybe. Get big. There we go. Okay. So we've got a circle around here. We know the circumference is 2 pi r on there. In case you've forgotten geometric things, this is also on your reference table because, well, we like keeping all the simple equations on here. So for wire radius B, the inner one, then the circumference would be 2 pi b. And that is the length of our wire. We know R equals rho L over A. And they told us in the question that this is the same kind of wire, which means to me, I'm going to assume that the rho value and the A are both identical to each other. So it's the same rho, which means I don't need to worry about it, and the same A going on, which means my resistance is just proportional to the length of the wire. So to begin with, when my length was L, I got a resistance R. Now that I have a different one, I have a length of 2b, or sorry, a radius of 2b in here. My circumference is now 4 pi b, which is 2 times the length. All right. So 2 times the length should mean that I have a resistance of 2R as my answer. Now, why is it not 4R? Well, the R in the circumference equation wasn't squared at all or anything special like that. So simply doubling the radius will double the circumference, which will double the resistance. Okay? If we were looking at changing the area of the wire, then we'd have an R squared, and there'd be a factor of 4 going on there as well. But we don't, so it's just a squared sort of, not a squared, just a doubling sort of thing. All right. That one makes sense? Okay. All right. So let's go back to this one. All right. Question number 2. A wire has length L and radius R, has a resistance of R, little r, big R. We take a second wire made from the same material that has a different length and a different radius. Okay, this is where we are getting a little bit more confused in here just with terminology. If you want to imagine this little marker as my wire, when they talk about radius in this question, they're talking about the radius of the circle, the radius of the cylinder itself. Unlike the previous question where they're using R to talk about the radius of the loop. So this is simply L, length of the wire, and R, radius of this wire. Okay. So we're going to do the same sort of thing going on here. We have a wire length L, radius R, resistance big R. We're going to take the length and cut it in half. And we're going to take the radius and cut it in half as well. What's going to be the outcome for the overall resistance? Take a minute, ponder some math, and we'll see how we do. All right, 1 vote for B. Katie thinks it's B as well. Lots of votes for B's. All right, and survey says I got B as well. All right, so nice. So because A equals pi r squared, cutting the length in half reduces the resistance by half. Taking the radius and cutting it in half makes the resistance 4 times bigger, 1 over 1 over 4. So you combine the two changes together, half as much from the length, 4 times as much from the radius, and gives us double the resistance in that circuit. All right, cool. Good job. All right. And in case you haven't gotten the hint yet, a lot of the questions that deal with radius and length and resistivity are going to be this kind of question, where it's what happens if we double this or triple this or stuff like that. Very similar to the questions you might see with Fg equals gm1 m2 over r squared sort of stuff for gravity of planets or forces from charges. The double this, triple this, what happens sort of stuff. All right, let's move on to the next one then. This one, not about lengths and areas, excuse me. This one is we have a variable resistor, so a device that we can change the resistance of. And we connect it across a constant voltage source. Which of the following graphs shows the power dissipated or given off by the resistor as a function of the resistance? So as I crank the resistance up, what happens to the power? All right, take a moment, throw up some guesses, and then we'll talk through this one. B, A. A question mark, A maybe, yes. Okay, so we've got a good group so far saying A. A few people haven't chimed in yet, that's fine. Give yourself a second to think about it. And let's talk through the process for this. So I'm going to go back to the paper for a second here. So we're going to stop this. We're going to switch to the camera. And, all right, so ignoring the last question, that's old. All right, so for this one, we know, right off our reference tables, power is current times the change in voltage. And that's great. That is the equation that the AP says, hey, we should probably know what this is. Super. The problem is I don't see an R anywhere in this equation. It's not in the I, it's not in the V, and it's not a P. I like P because I need to have that on my y-axis, but I really want to have power and resistance. And that's a problem because I don't have current at all in here. I don't have voltage in here at all. So this is where we can grab Ohm's law. On your reference tables, it's defined as delta V over R. I memorize it as V equals IR. Some of you guys may have learned it as R equals V over I. It's all the same thing. It doesn't matter which one you choose. Okay, but the thought here is that I can now plug this in for I. Take that, plug it into there, and I will get power equals V squared over R. And this is good because now I have a resistance in here. Now, some of you are saying, well, sure, but couldn't I have also solved this for V and said V equals IR and got power equals I squared R? And absolutely you could have. And that may be very valuable in a future question. But the reason that this one is better is because in the question, they told us the voltage was constant. And if the voltage was constant, I want the one with the V in it because I get to ignore that. I say power is proportional to 1 over R, which should look like our inverse graph, which is choice A. If the question had said current was constant, I would have gone with this one. And we would have said, okay, so power is proportional to the resistance. I would have gotten a linear graph out of that. So depending on what is constant in the question drives which relationship we're going to choose. Are we going to solve and get rid of the I? Or are we going to solve and get rid of the V? We're going to get rid of whichever one is not constant in our reaction. All right. Questions on that one? All right. So I've got one more question to do, and then we can move on to wrapping up Q&A and stuff like that. So this one is a sample free response question that kind of made up just because this is a great topic to do for an experimental sort of question. This, if it was on the AP, would probably be one of those 25-point questions. No, sorry, 12-point questions, 25 minutes to solve. We don't have 25 minutes to solve, so we're going to kind of condense this down a bit. But let's take some time to think about it, because based on this stream today, you guys have all the tools you need in order to solve this given experimental task. So, reading through this, a student wants to perform an experiment to calculate the resistivity of a piece of wire. So we're going to give you a random piece of wire and say, hey, find the resistivity of this wire. We want to design an experimental procedure. To figure it out, assume you have access to typical laboratory equipment. So whatever sources of stuff you would need, you would find in a common lab situation. And we have to start off listing the measurements you will be taking, the symbols used to define them, as well as the equipment we used to make the measurements. All right, so let me back up a bit here. Resistivity, if I look at my resistance equation here, there is only one equation on this side that has resistivity in it, rho. So I want to find this little rho guy right here. I need to know length, area, and resistance. So area, definitely. Length, okay, yep, I can do that too. Resistance might be the tricky one because I don't have a good tool for measuring resistance in a common lab situation. Area, sure, maybe I use some calipers or a really good ruler to measure the length or the circumference or something like that about the wire. Length is easy. Use a tape measure, use a meter stick, something like that. That'd be fine. But to measure resistance, I may have to go through and do the next equation, I and V. Yeah, I'm going to do I and V as well, then use Ohm's law to get R, use R to get rho, and then we're good. So this is a pretty common thing to do in experimental questions, where looking at the equations kind of tell us the way that we need to go in order to get the question done. So in this case, let me start writing stuff out here. Where's my cursor? All right, so we need to figure out and make a table here. So let me write down my table so it'll look all pretty and jump back in a second here. So I'm going to measure. I'm going to need the symbol. I'm going to need the term. Or not equipment. All right, so this is my very nice, super awesome thing here. We are going to measure area. Actually, can I measure area directly of a wire? I don't think we can. So maybe not area. Maybe diameter or radius or circumference, something along those lines. I'm going to say radius right now. because that's going to make life easier in the middle. It'll be a small r. And my equipment, I'm going to use a caliper. Okay, for those of you who haven't used a caliper before, don't know what I'm talking about. Basically, it's a very fancy measuring device that you take two pieces of metal, typically scrunch them together, and then you can read the value of the distance between it. I use a bunch of digital ones in my lab, which will tell you the diameter or the radius in centimeters or millimeters or whatever. And they're typically accurate to 10 to the millimeter on there. So they're a pretty good tool for measuring really small distances on there. We're going to measure the length. I'm going to call that L, and I'm going to use a ruler for this. Depending on what's going on, meter stick, tape measure. You could use a caliper too if you really wanted to. They go out, but yay big. So depending on how long your wire is, you've got some options there. We're going to measure current. That's capital I. I'm going to use a multimeter for this. You could also use an ammeter. It doesn't really matter. Multimeter is nice because that's what I've got in my classroom. Basically, it's an ammeter and a voltmeter in the same device. So it's one thing instead of two separate ones. And we want to measure voltage. That'll be V. And again, I'm going to use a multimeter or a voltmeter. All right, and there is my list of stuff that we need to measure. Continuing on here, the next part of this says that we need to get back to the question. Okay. Describe the procedure to be used to determine the resistivity. Provide enough detail that someone else can replicate it. Are we allowed to just draw that chart? Well, so Jennifer, it really depends. Like in this one that I'm modeling off of, the question actually would have had a chart in there for you to fill out. So part A doesn't say anything about doing a paragraph for it. It just says make a list. So we have made the list. We have checked that box and said we're good. Part B, where I was talking about describe the procedure, that one sounds like a paragraph because I really can't do a table or a list there like that. So part B really says procedure, written out paragraph form. And then when we get to part C, that's also going to be describe how the data. So we're looking at, again, for some sort of paragraph response for that in there. So part A, I would be okay with either one. And I think as a rater, I would be okay however you want to describe that sort of stuff. But just be aware that if the question talks about a paragraph, go for it. If it doesn't, you got a little bit more leeway on there. But it also never hurts to over-explain what you're doing on there. All right, so part B, describe the procedure that could be used. How could we figure out the resistivity using our measurements, use the symbols, and or include a diagram of the setup? All right, so for this one, I'm not going to write out a whole paragraph. Sorry. This would be a great time to do it, but let me talk about the things you should include in this part B response. Just for the lack of time, I'm not going to write out the whole full-blown paragraph here in there. So there's part A. Part B, I'm going to do bullet points. And then, again, if this was the exam, let's flesh this out into a full, good paragraph response for it. But basically, we're going to take the wire. We're going to measure the radius and the length. So far, so good. We're going to hook it up to a battery. And then measure I and V. And my sample circuit, since they asked for a drawing, would look something like this. Okay. That resistor is the wire we're trying to test. The A is the ammeter. The V in a circle is the voltmeter. And of course, we've got our battery hooked up to it as well. So there's my sample circuit here. The other thing I would do is then shorten the wire. Maybe only clip part of it in or move the connection points a little bit so I make the wire shorter and repeat. Okay. Something really good to get into pretty much every single experimental design question you guys do is always do repetition. Always take multiple measurements. Always do multiple scenarios because that's the way you're going to reduce the experimental error. So I guarantee you, if this was an AP question, one of the points on this part's scoring would be for multiple trials or multiple repetitions. In this case, I'm doing different lengths of the wire. Okay, you could do different areas of the wire. It actually doesn't really matter as long as you are choosing something that you can make different. You could even do multiple voltages. Actually, that's probably even easier to do, is to add another battery in, and repeat, and do V changing on there. That sort of part is kind of what you're looking at here. So you're going to take it, you're going to measure these guys using the tools, put it in a circuit so you can measure the next parts, change something about that circuit, and then repeat. So I was going to change L, actually thinking about it and talking it out. I really want to do more batteries. And then repeat 5 times, 10 times, whatever is a good experimental number. You guys have been doing experiments throughout this course. I feel like you guys should have a good feel for how many batteries or how many trials we should do here. I'm going to say we're going to repeat with 5 different voltages. And if you are in the camp that says more, make it 10. It's okay. I wouldn't do 1. I wouldn't do 2. 3 is pushing it a bit. 5, 10, 7, somewhere in that range is probably where we want to be for that sort of paragraph response. All right. And again, take this, make it a very pretty, nice, easy to read, organized, drawn out procedure, paragraph response. Okay. Again, I'm not just for time's sake, but if you're interested in that sort of thing, we can definitely talk. Talking Wednesday, actually, for the Q&A stream at 1 o'clock. We can go over writing paragraph responses really easily for a bunch of these questions too. All right. And finally, the last part on here is going to be describe how the data could be used to determine the resistivity of the wire, include equations where appropriate. Okay, so now I've got this data. You can imagine I have this giant data table that has R, L, I, V, all sorts of data in here. How the heck am I going to get the resistivity out of it? Well, I'm going to go back to what Marshall said earlier. We're going to go to our equations. So I know R equals rho L over A and R equals V over I, or I equals V over R, whichever Ohm's law variant you want to do. Well, what this means is that V over I must equal rho L over A. Okay, this is looking pretty good. My goal here is basically to get this in the form of a linear relationship. And once I get in that form, I'm going to graph it. So V is, in my case, what I'm changing. Now, if I was changing L, for example, I'd rearrange this to get L equals something. But in my case, because we said we're changing V, this means rho L I over A. Okay, so if I am measuring V, what's the other thing in this list? As I change V, what else of my measured values should change? What's the other one that would make sense to graph on here? Well, Did we change the radius of the wire at all? No, I kept that the same. Did I change the length? Well, I was going to, but then we said, no, we're going to stick with the voltage. So the length stayed the same the entire time. Voltage went up. Current's got to be the other thing that changes. So I want to make a graph of voltage versus current. If I do this right, again, we got our y equals mx sort of relationship here, where voltage is on the y, current is on the x. That means that everything else, rho L over A, must be the slope of that graph. So if I graph this, it gives me a straight line relationship. The slope will equal rho times L over A. So how am I going to do this experiment? I'm going to graph V versus I. I'm going to calculate the slope of the best fit line. I'm going to set that best fit line equal to rho times L over A and solve for rho. And there is my description of how I'm going to use the data to find the resistivity. With equations, 1, 2, realistically, you could do this one too and say this is what it's equal to. That's perfectly fine too. But that's what would give you credit for that one. And on the AP, they would love to see the words graph or plot in the answer, because if you're doing multiple trials, typically they're going to want to see multiple graphs and stuff like that. Wow, that pen's broken. That's great. Okay. All right. So on that note, it is 8 o'clock. Are there any questions that I can answer quickly before we call it a stream? All right. Well, you're welcome, Katie. Thank you guys all for attending. I hope to see you guys next week, same time, same place, for Circuits Part 2, or 1 o'clock Eastern, whatever that is in your time zone, for Q&A and stuff like that. Have a great night, guys. Thank you very much. Or Marshall, I'm going to link the slides to the end of this stream. So if you click the stream stuff, there should be a link at the bottom for accessing slides and stuff like that. All right. Have a great